Hello, I am Dr. Uksun Kim. In this video, we will be discussing the truss analysis using the method of joint. This slide shows the overview of my lecture. In the beginning, I will talk about the definition of truss. Then you will learn about the free body diagram for joint, zero force members, and method of joint through an example problem with detailed explanation. Finally, I will provide a practice problem to check the level of your understanding related to this topic. A truss is a structure composed of members joined together by pins at their endpoints. There are two assumptions for truss analysis. The first one is all loads are applied at the joint. Okay. And then second one is the members are joined by pins. And then the members act as two force members that they are loaded in either tension or compression. So you can say this is the tension, right? And then the compression of the member. This slide gives the important guidelines related to the free body diagrams for joint. The equilibrium of a joint needs to be considered. All forces acting on a joint should be included in a free body diagram. All dimensions should be included, such as distance, angles, etc. Then assume that all unknown member forces act in tension. There is a pulling on the pin or outward arrow from the joint. This is very important. Okay, so draw the free body diagram of the joint. You need to assume the unknown member forces in tension. So that means that you draw the arrow, outward arrow from the joint. And then a free body diagram of each joint should be drawn. This slide shows an example problem. So let's draw free body diagram for an entire truss and then free body diagram at joint F. Okay, so first thing, draw the free body diagram of the entire truss, and then also try to draw the free body diagram at joint F. So free body diagram for entire truss, you can see that this is the A is the pin support, C is the roller support. So you just draw the free body diagram. The entire truss, right? And then each is connected with a pin, okay? And then that is the 10 kilonewton. There's an external loading. And then for the support A, there's a pin support. That one is at the AX and AY. Okay? And then also C, there's a roller support. So that one is at the CY. Only one reaction for the roller support. And then you also put the dimension. So that one is at the 4 meter. And then also 3 meter and 3 meter. And then also don't forget external loading, another one at the joint B, there's a 30 kilonewton. And then that is the free body diagram for entire truss. And then the free body diagram at joint F, okay? Now we draw at the joint F, so we need to isolate this one. So you draw the free body diagram and then put the external loading, there's a 10 kilonewton. And then this is very important. There's all the member forces assumed one is the intention. So that is the arrow is at the outward from the joint. So there's assumed tension. So there's a F and then F, E. There's a F from to E. And then there's a outgoing. And then another one is that the vertical one, there's a F, FA. There's the same thing, there's a outgoing. So this is a free body diagram at joint F. So there's a way you can also draw the free body diagram at a joint also. This slide provides the ways to identify the zero force members. The first case is that if a joint has only two non-collinear members. Non-collinear members, this is a collinear one. So this is a non-collinear members and there's no external load or support reactions and that joint, then those two members are zero force members. So in this case, this member, this member, this member, and this member is the zero force members. And then also another case, if three members form a truss joint, for which two of the members are collinear, there is no external load or reaction at the joint, then the third non-collinear member is a zero force member. So in this case, this one and this one is the zero force members. This slide for the example problem, and then now we try to identify zero force members. So to identify the zero force members, and then this one is a zero force members, because you can easily see that from the free body diagram of the joint F, we previously draw it, the sigma Fy equals 0, so that member should be 0, right? And then this one is that also non-collinear member, so this two is also zero force members. So that is that the F, FA, F, DE, and F, DC. That is the zero force members in this example. This slide provides a step-by-step procedure to find member forces using the method joint. Step 1, if the truss support reactions are not given, draw a free body diagram of the entire truss and determine the support reactions. But there's only need this kind of procedure. So sometimes you don't need to find the support reactions. And then you can also find the member forces without the support reactions. So this is the optional procedure. And then step 2 is to draw a free body diagram of a joint. Maximum number of unknown forces at each joint should be 2. Okay, there's a value should be 2, because only 2 equations of equilibrium can be used for method of joint. So that is that the sigma fx equals 0, sigma fy equals 0, but this is a connect with a pin, so sigma m equals 0, you cannot use. So there's only two equations you are able to use that. So there's a maximum unknown forces for each free body diagram should be 2. There's a maximum number. Step 3, apply the equation of equilibrium. There's a sigma fx equals 0 and sigma fy equals 0 to determine the unknown member forces. If the answer is positive, the assumed direction, we assume in tension. So assumed direction is correct. That means it's a tension. Otherwise, it is in opposite direction, there's a compression. And then we already learned about the truss member is a two-force member, tension or compression. So we can decide it based on this rule. And then step 4 is to repeat the steps 2 and 3 at each joint in succession until all the unknown member forces are determined. So this is the analysis procedure for method of joint. In this one, let's find the reactions using the equilibrium equations and the member forces using the method joint. Okay, so this is the free body diagram. We already draw it. Okay, there's a free body diagram for the entire truss. And then with this one, and then using the equation of equilibrium, we can find the unknown support reactions. So sigma MA equals 0. We use this one, and then once again, the counterclockwise moment, there's a very important, there's sign convention. So in this case, the pivot point is A for the moment. So AX and AY cannot create a moment. And then 10 kilonewton, moment arm is 4. And then with this force about the A, and then rotate in the clockwise. So that is a negative sign. Okay, so 10 times 4. And then 30 kilonewton. This one is at the also moment arm is at the 3 meter. And then there's a clockwise. So there's a negative sign also. And then CY times moment arm is at the 6, total length 6. And then that one is at the counterclockwise. So there's a positive sign. So with this kind of formulation, you can get the CY value directly. So that value is at 21.67 kilonewton. And then there's the same as the assumed direction. So there's an upward, or maybe you can say that the 65/3 kilonewton. And then you can also use the sigma MC equals 0. In the case, your pivot point is at the C. And then AX cannot create a moment, CY cannot create a moment, but the AY able to create a moment about the C. So that one is at the AY times 6. And then this one about the C, there's a clockwise moment. So there's a negative sign. And then 10 times 4, there's the same thing for the clockwise. So there's a negative sign. And then 30 times 3, there's a moment arm. And the dead one about the C is that the counterclockwise moment. So there's a positive sign. And with this kind of formulation, and then you can get the AY value, there's a 8.33 kilonewton. That one is also same direction of the assumed, there's an upward, and then also as a fraction, 25/3 kilonewton. And then sigma Fx equals 0. So you can see that the AX and then this one, so AX plus 10 equals 0. So AX equals minus 10 kilonewton. Answer is a minus, means that this is the assumed direction. So actual direction is that the opposite direction. So that is that we can find all support reactions. This slide shows the solution for member forces using the method of joint. So this is the, once again, free body diagram for the entire truss, but for the massive joint, you need to find the member forces to draw the free body diagram of each joint. So first one is the free body diagram at joint C. So you need to isolate this one portion, right? And then in this part of that, C5/3, we find the CY value from previous step for there is a support reaction. And then FCB, right? FCB, and then you can see that one is at the outward from the joint. So they assume that force is in tension. And then FCE in this one, and then make sure that there is a small triangle. So that is the 4, 3, and this one should be the what? 5, okay? So with this kind of the relationship, so sigma fx equals 0, so that means that in this free body diagram, okay? In this free body diagram, minus FCB, okay? Because there is a positive direction of the fx, and then minus FCE 3/5 equals 0. So FCB is at this relationship with the FCE. And then sigma Fy equals 0. So that one is at the 6/5/3 of what? This one, right? So there's a positive direction. And then FCE 4/5 equals 0. So you can get the FC value from this one. So FC value is at the negative 27.08 kilonewton. So that negative means that what? There's a compression, right? And then FCB, that is a 16.25. You can plug in this value to this equation. You can get the FCB value. So FCB value 60.25 kilonewton. Positive value, that means that there's a tension. And then move on to the free body diagram at joint B. So this one, right? Joint B. In this one, you can draw the 30 kilonewton in the external loading. And then 6.25, we previously FCB value, we found it, there's a tension. So there's an outgoing from the joint, and that one is at 6.25, okay? And then there's two unknowns. There's a FBE and then FBA. And then we assume that in those forces in tension. So sigma Fx equals 0. So FBA minus, right? So this is a positive direction, plus 16.25 equals 0. So FBA equals 6.25. So there is a tension. And then FBE minus 30 Newton, kilonewton, so there's upward equals 0. So FBE is at the 30 kilonewton. There's a tension also. And then move on to the free body diagram at joint A. So free body diagram, joint A. And that one is at the 10 kilonewton. We found that one from the support reactions, and 25/3 kilonewton, this one. And then 6.25 kilonewton, there's a tension in the FAB. And then FAE, there's a unknown number of forces, and we assume that this force in tension, and then using the also small triangle, right? The 4, 3, 5. And then sigma Fx equals 0. So 16.25 minus 10, and then FAE, and then 3/5, okay, equals 0. So that one, you can find the FAE value is at the minus 10.42 kilonewton. So there's a negative sign. That means that the compression. You can find this same value in the sigma Fi equals 0 also. So there's a sigma Fi equals 0, 25/3, and then plus FAE 4/5 equals 0. So you also get the same value, FAE equals negative 10.42 kilonewton. So negative means that the compression. And then finally, free body diagram at joint F. And then you can draw this one is the free body diagram for this one. So there's external loading is 10 kilonewton. And then assume there's an intention for the FFE and then FFA. So sigma Fx equals 0. There's a 10 plus FFE equals 0. So your FFE equals minus 10 kilonewton. So that negative sign means that the compression of the dam member. Okay. And then sigma Fi equals 0. So there's only one component, there's a FFA. So sigma FFA equals 0. So we already know that from the previous 0.0 force members. So this is a 0 force member. So we confirm that, right? So we know that this kind of thing. So that is all the member forces. You can find it using the method of joint. This slide shows the practice problem. For this practice problem, this is very important. You don't need to find reaction forces because you can find the member forces starting from the joint D. So you don't need this kind of A and B step because you start from draw the joint, the free body diagram at the joint D. You can see that there's only two unknown forces, right? Here and here, right? So that's the reason why you don't need to find the support reactions in this case. And then also, there is no zero force members in this case, so you don't need to worry about the C also. So you just using the D and the E in these two things, and then you can find the member forces of this truss. I hope this video is helpful for you. Thank you.